Very good. Welcome back. What I want to discuss in this next half of the lecture is having decided what entropy we are supposed to maximize, what are the constraints that we are going to impose on that maximization process. So the question then becomes, of course, the constraints are supposed to incorporate, codify the information that happens to be relevant to the particular problem you're trying to handle. So it is particularly crucial to identify the relevant constraints to a situation. In this particular case, we're going to be dealing with situations of thermal equilibrium. And the processes we're sort of interested are those processes in which we manipulate macro states. We don't have the power to go and mess around with individual atoms or things like that. You can change volumes, or you can change external fields. So the macroscopic processes that you perform in order to do a macroscopic control of the macro state. So first, we're looking for equilibrium. So if a situation is one of equilibrium, it means that things are not changing. So we seek situations in which the probability distribution on phase space is actually independent of time. What this means is that the Poisson bracket of that distribution with the Hamiltonian is supposed to be zero. Another way of saying this is that whatever constraints we're going to impose have to be constraints that apply to equilibrium. They're not changing over time, and so we need the constraints will involve constants of the motion. Whatever this probability distribution depends on, it has to be something that is a constant of the motion. For example, an energy. F is going to turn out being something like e to the minus beta e. Well, that is the energy. So whatever the F depends on has to be constants of the motion. Very good. But this is not enough, because we have many constants of the motion. We have energy, we have momentum, angular momentum, we have a number of particles. So there are quite a few things to pick from. So here we're going to impose we're going to limit our system of interest to situations in which the probability distribution is not just constant in time, but it is also what's the word? It's not just static. It's not. I'm sorry. It's not. It is static. It is not just stationary. So we want to rule out situations in which you have the system rotating as a whole. So and you also want to rule out situations in which the system is moving with a certain momentum, right? Rotations, overall motion of the system. You want to rule those things out. When you study a system in thermal equilibrium, typically you have it at rest in your lab. You don't have to chase after it. If you did have to chase after it, then you would choose a reference frame with which you're moving with the system, right? So we want to eliminate momentum and angular momentum as the constraints on the on the probability distribution. What that really implies is that these constraints on the total momentum being zero and the total angular momentum being zero are going to be achieved naturally. If you have a gas and you impose a constraint on, say, the total energy, then automatically the number of particles moving to the left and the number of particles moving to the right is going to be the same on averages. And so what that means is that the total momentum is going to turn out to be zero. You don't have to worry about it. Same thing with angular momentum. The number of particles going one way matches the number of particles going the other way, and angular momentum will turn out automatically to be zero. If you want, however, to include momentum, angular momentum, or even the number of particles, we will also assume for the time being that the number of particles is fixed. Later, we will see how you include possible changes in the number of particles. But to simplify, let us just focus on the simplest possible situation in which energy is the conserved quantity of choice. But you probably appreciate that we've been limiting the kind of problems that we've been tackling, right? We don't allow the number of particles to change. The momentum will eventually turn out to be zero momentum overall on the average. All of those things will end up happening automatically. But even if we decide on a constraint in the energy, we know that the energy is conserved. Good. This suggests to pick a constraint on the expected value of the energy. But notice the following: if the energy E is conserved, so is E squared. So shall we use the expected value of the energy squared as a constraint as well? In fact, any function of the energy is conserved too. Shall we then use functions of the energy like that? So you see what I'm going for here. While it is true that we can argue fairly easily, the energy is a conserved quantity, F should depend on the energy, so we need a constraint on the expected energy. This argument does not at all rule out the fact that you could have any function of the energy being the appropriate constraint. So the question is, which function? What's sort of interesting about this mode of arguing is that you're going to realize that we will get that the appropriate quantity to use as a constraint is the expected value of the energy. We will get that. But that's going to require more assumptions that further delimit what kind of problem you're dealing with. If you change those assumptions, you're going to realize that, oh, maybe we need other constraints as well. So let's proceed. So how does this work? What we're going to say is there is a way to actually figure out how to handle this problem. And when we say is, imagine, let's be very clear now about what we mean by a problem of thermal equilibrium. You have a system A, and you have this system in interaction with another system, a bath, a thermal bath, that we're going to call B. And the assumption we're going to make is that this is all there is. The system A interacts with its surroundings. System A is the system of interest. B is the bath. Now, what do we gain from having something like that? What we gain is that the composite system composed of A plus the bath, and this is the composite system, is isolated. Once we included the bath together with the system of interest, the composite system is isolated. And if the system C is isolated, therefore, the energy of the composite is constant. It's fixed. What that means is that the expected value of the energy of the composite is just going to be itself. It's not fluctuating, it's nothing. It's whatever it is, we shall assume it's given. And if you were to do the square, then this is also known. It's fixed. And if you were to do any function and do the average, this is going to be the same function. So the assumption that we're using here is that we may not actually know what the actual expected value of this is going to be, but we're going to understand that this is the piece of information we need in order to make further progress. We're going to proceed as if we have it, and if in the end we need to still look for it, we will. Of course, it's going to turn out to be the case that we're not really going to need to know the detailed number here. We just are making use of the fact that whatever it is a constant that doesn't change in time. Very good. So now, let me, having said this, let us say we have to maximize the approach I'm following here before we proceed. This approach is based on what is called the micro-canonical ensemble. The idea that we deal with a system that is isolated and therefore has constant energy. That's called the micro-canonical ensemble. To proceed then, we're going to assume, let me see, what else we need to do? We have the system C, and it has an energy, and then we're going to say, yes. We reach the conclusion that our system A is going to be coupled to a bath, and the system of interest here is going to be C. What are the microstates of A? Okay, let's talk a little bit about what microstates we're going to use. We want to maximize an entropy, dz f z log f z, where z now is going to be like the phase space for the whole composite system. So what we're going to do now, you see that I'm using the equal a priori probability theorem, right? Divided by a constant which I dropped because it does not affect the maximization. Very good. What we're going to do to simplify, this is not strictly necessary, but to simplify the discussion, we're going to divide phase space into cells, and the cells are going to be such that the probability of a particular cell is going to be the probability density in that cell multiplied by the volume of that cell. And so instead of maximizing this entropy, we can write this as maximizing the entropy over all this discrete probability distribution over the cells. Very good. At this point, we're going to further make one important consideration here, which is how do you describe the microstates of the composite system? Important. The microstate of the composite system is going to be described by saying that system A is in microstate A and the bath is in microstate B. This sounds very, very innocent. You have the composite system, and how do you describe the composite system? You just describe the state, the microstate of each one of its parts. Sounds innocent, but this actually does not allow you to have a quantum mechanical system A that is entangled with a quantum mechanical system B. So when you have entanglement, when you have a system that is entangled, a quantum mechanical system that is entangled, you cannot describe it in terms of the properties of the one part and the properties of the other part. That's the essence of entanglement, right? So when we say something like this, it's immediately saying that the systems here are unentangled. They can be correlated, but there is no entanglement. So that's the first thing. The other thing is that because we know that the total energy of the composite system is E, we are going to make the assumption that system A and the bath have energies EA and EB that's such that the sum matches the composite. Now this is also very, very simple and looks intuitive, but in particular notice that there is no interaction energy. There is the energy of A and the energy of B, and this only depends on the state of B, only depends on the state of A. There is no potential of interaction. So what we are saying here is that when you have your system A and your system B and you put them together, they're going to be essentially non-interacting. A and B have very weak interactions. This is what allows you to separate A and B. Whenever you have a system A that interacts strongly with a system B, you can't really even separate them. They're interacting so strongly that it's really just one system, right? The reason that whatever allows you to say this pen is a separate system from my hand is precisely the fact that the parts of my hand are interacting strongly with each other, the parts of the pen are interacting strongly with each other, but the parts of the pen and the parts of my hand are not interacting that strongly, so much so that I can pull them apart very easily, I can slide them, I can do all sorts of things, right? So the interactions here to be very weak in order to be able to do this. I'm neglecting all the surface tensions that account for interactions. Have to be very weak, but not too weak. You see, this is always tricky. Have to be weak, but not very weak, not that weak, because if it were that weak, then these two systems are completely if they are completely non-interacting, they cannot exchange energy, and therefore they can never reach thermal equilibrium. So they have to be weak to allow you to talk about two systems. but not that weak that you will never reach equilibrium. So these two conditions here that seem like so trivial are they're kind of tricky. Very good. So now that we are we've reached a point where we know what are the microstates for our system, we are ready to start maximizing the entropy. And in order to do that, and this is the real reason why I drop back into a description in terms of cells, let us just count the total number of microstates of the composite system C. Let omega C at energy EC be the total number of microstates of C with energy EC. Then what I'm going to claim is that the total number of states with energy EC can be written in terms of the total number of states of the system B when B, what is the energy of B? The energy of B is going to be EC minus EA. So the total number of states of the composite system is going to be the total number of the bath when the system of interest is in the microstate A, and then I'm going to sum over all possibilities for the system A. So A labels each one of the microstates of A, and so when A is in A1, there's going to be a certain number of microstates of B. When A is in A2, there's going to be a certain number, and so on. Add over all values of A1, A2, A3, and so on, and you get the total. So this is the first piece of the puzzle. What we're going to say now is we're going to find out the probability distribution of the state C. What is PC? For this, we maximize entropy. So maximize the entropy of state C minus C PC log PC subject to, well, the only constraint we have, right? The only constraint we have is that the states that we're considering here are such that the energy is equal to some value EC given. So basically what is this? This is telling us that is the energy, which means immediately that PC is going to be 0 unless the energy of C is this value EC. How about the remaining ones, the ones that do match the energy? For all of those, we have this number. So maximize entropy. What you get is a uniform distribution which says that the probability is a constant. This is the constant that we have there. for the energy of the state being EC for those C such that the energy is C, zero otherwise, and the entropy of this maximization is just going to be the log of this number. So this is the place where we do the maximum entropy. And the maximum entropy is basically say, look, get rid of all the states that you know are not there because it's the wrong energy, EC, not EC. For the remaining ones, it's just going to be uniform over those. That's all there is to it. Very good. Once we have that, we can actually calculate what is the probability of A being in a microstate A. Because how do you achieve A to be in a particular microstate? You take the probability of A, let's see, for the whole system, you have A and B. This is the joint probability for A being, the system A being in the microstate A and the bath being in microstate B. This is what we call PC. And we marginalize by summing over all the B's. Now this is one of those interesting manipulations of probability that we learned at the very beginning. When you have a system composed of two parts, to compute the probability of one part, you just take the joint probability and marginalize. But this PC, we know what it is 1 over EC. So what we have here is a constant, and now we're summing, and it's a constant and it's independent of B. So what this tells us is that we're going to have A is going to be this constant, that constant, and you sum, you multiply by the number of microstates B. So you have to multiply by the number of microstates that have the appropriate energy. And this is the important quantity. This is it. We have the probability of PA. What do we do next? Very well. At this point, we're stuck. We need more assumptions. What else do we know about the particular system A and the bath? Well, one thing we know, so we need more information. And the piece of information that I'm going to introduce here is actually rather non-trivial. And it's typically that the bath tends to be much bigger than the system A. The idea is you have a system A in thermal equilibrium with the environment. The environment is usually much bigger, and this manifests itself in saying that the bath has typically energies that are much bigger than the system of interest. Or because EC is EB plus EA, the energy of the whole is going, bath plus a system, is going to be much bigger than A. So what this allows us to do in this distribution here is we can compute or approximate the number of states of the bath by doing a Taylor expansion because EA is much, much smaller than EC. Highly non-trivial. 1 and 2. The other thing we need to do is the bath is not just much bigger than system A, it's big. The bath is large. And what that is, we're going to represent that is by saying that omega B ED is a function, the number of microstates with energy EB is a function that increases very rapidly with EB. In fact, typically what ends up happening is that the number of states grows like with an exponent of EB that's actually very large, right? It's a combinatorially large, like a factorial or something like that. So the bath is large, much larger than A. That suggests a Taylor expansion. But omega B changes very quickly. Even for small changes here, it changes very quickly. So just doing a Taylor expansion is not going to work very well, because Taylor expansions sort of assume that if you change the argument by a little bit, the function will change by a little bit. But if this increases very quickly, that's not going to work. So the way what we handle this is we say, instead of expanding omega, expand the log of omega, because this is a function that varies much slower. And so we're going to expand this quantity, and when we expand, we're going to do the log of omega B evaluated at the point C plus the derivative of this quantity, the derivative of this quantity EB with respect to EB evaluated at the point EB equals C, and we're going to call that beta. So we have the derivative and then multiplied by the small displacement here, which is minus beta E. And because the bath is so big, we're going to neglect higher order terms. Very good. Now that we have something like this, we can actually take exponentials. This is going to be equal to the exponential omega B epsilon C, the exponential of minus beta EA. And if we come back to this expression that we have here, we're going to divide, we can find PA by dividing by omega B EC, omega C EC divided by omega C EC. So now these are, whatever these objects are, of course we have no idea what precisely they are and all of that. But it's very clear now that because this is independent of A, we can just compute that overall constant as being the normalization constant, and this is our distribution for our probability distribution for the system of interest. Sort of amusing. Oh, look at this. This is an interesting interpretation of what the partition function is really doing. One interpretation is the partition function is just normalization. Fine. But it's also true that when you compute the partition function, it is telling you something about the relative degrees of freedom of the number of states of the bath, the environment, and the number of states of the bath plus the system of interest at the same energy, you see. It's also remarkable that we didn't know much about the note. We need not know much about the bath. Only beta, only that coefficient. That's the only thing that really enters in our description of what's going on with the bath. The bath is something that's out there. The only thing that we need in order to describe it is beta. So now you can see that now that we have the probability distribution, even if you do not know what beta is the object you need to find out in order to have a good description. Let me see. What can we say here? We're done. So now let me comment on what it is that we have done. Because maximizing S PA log PA subject to a constraint on the energy. Let's call it like that. The energy of A, yes, let's put it like this, E A, right? Because maximizing this entropy subject to this constraint and, of course, normalization gives exactly the same distribution Now we conclude that this is the constraint that is relevant to this particular situation. So you see that we have approached the problem kind of backwards. Our goal was to figure out what the constraint was. And we have no idea what the constraint is going to be. It's going to be some energy, okay, but we do not know if it's going to be the energy squared or any function of the energy. What we did was let us focus on a situation where we sort of know what the answer would be, because if the system is isolated, then we know the energy is given, and both the energy and the energy squared and all that, we know all of those. So by focusing on the system coupled to the bath, we sort of know a little bit more, and we realize that the distribution we get in that situation under certain assumptions is precisely what we get when we impose a constraint on the expected value of the energy. This justifies using the energy as the constraint for maximum entropy calculations. Have we gained anything here? Can you just say, look, you just use the microcanonical ensemble and you don't need MaxEnt? Well, we have gained. What we have gained is the appropriate entropy that we are using invokes the equal a priori probability theorem. We did not have to invent that out of nowhere. We proved that. Second, we realized that this sort of expression which is derived by having the constraint on the expected value of the energy, that did not come for free. It was necessary for the system to be unentangled. It was also necessary for the system to be weakly interacting, but not too weakly. Then we also came up with and that allowed us to compute, right? We used the method of maximum entropy and it allowed us to compute. Perfect. But then we also had to assume that the bath is much bigger than the system A, and the bath is supposed to be large enough that omega b, the number of microstates of the bath, increases very rapidly with its energy. It's very interesting that we can therefore draw the conclusion that if your system, if the bath is small, then the constraints on E is not enough. You may need to include constraints on E squared, perhaps. You see, this opens up an interesting possibility. Can we generalize the canonical methods of doing finding the Boltzmann distribution? Can we generalize them to situations in which the bath is not large, small? How could that come about? Well, here is one possibility. Imagine that when we say something like this, the interactions between A and B are so small that the system A never reaches full thermal equilibrium with the whole bath, but it also only reaches thermal equilibrium with a small part of the bath. Under those circumstances, the distribution that you get is still going to be given by something like this. But the assumption that the bath is much bigger doesn't kind of work, because the system is not even aware of the other parts of the bath. It's only aware of a small part. So then the distribution is not going to be Boltzmann. So can we envisage doing non-Boltzmann distributions for situations in which the system is reaching equilibrium so slowly with the rest of the bath that it's only equilibrium with its vicinity? That is the kind of problem that may be very relevant in problems in, say, nanoscience, where things are happening quickly in a computer, but you are only in equilibrium with the bath in its immediate vicinity. So by being very careful with what are the various hypotheses and assumptions that are needed in order to derive that the expected value of the energy is the correct, relevant description of thermal equilibrium, we see that we have a handle on how to generalize the method of maximum entropy, tackle problems that go beyond the usual thermal equilibrium. Next time, we're going to deploy this to do the canonical ensemble for statistical mechanics. See you then.